Okay, YouTube, in this video we're going to explore graphs of polar equations, most specifically circles, but kind of give an introductory synopsis of what we know about polar curves and how we kind of conceive of them. So let's go ahead and start with this. When we look at graphs of polar equations, recall that what we're doing now is we're saying that we have a bunch of points r comma theta, like some distance from the origin, or what we call the pole, and in a given direction. So that being said, what we're saying is we have some r, which is our distance here, is a function of the angle that it's sitting at. So the first thing that I want to kind of denote is that when we talk about these graphs, if it is r is a function of sine, we're going to use a lot of functions with sine in them and cosine in them. But if r is a function of sine, it is dependent upon sine, then we're going to say that it has symmetry with respect to the vertical axis. So when we talk about the polar coordinate grid, sorry about this being rectangular, but I guess what I mean here is this. This is our vertical axis. So we'd say functions of sine are going to be, symmetrical about this axis here. And we say if it's a function of cosine, I suppose we could use a different color here, like this one right here. I don't know. We could say it'll be symmetric with respect to the polar axis. So remember, we call this our polar axis here, but functions of cosine will certainly be symmetrical with respect to that. So that being said, let's go ahead and take a look at the most basic probably polar graph that we can make here, but graphs of circles. We often spend a lot of time looking at those and their properties. So the very first one here, we say r is equal to a. I'm going to say a is some constant. So just for a matter of graphing this, what I'll say is, well, what if our function is r is always 3 no matter what? But the thing here is this: when we look at these things today, we're often going to be looking at just key characteristics, like what are the zeros of this? I guess I don't need an arrow there. But what are the zeros, and what are the maximum r values this will obtain, and what angles do special things occur? But for right now, what we're going to say is this: we have some angle and an r value that depends upon it. So in terms of what my angle could be here, we could say my angle maybe starts at 0 and then is going up by pi halves every time. It is here, and then I guess at pi, 3 pi halves, and 2 pi, and we would just go plug all of these into the function. You'll notice here that this is maybe missing a theta. So when we plug all of these in for our angles, the thing here is that the only solution pairs that are going to satisfy this are the ones that have r values of 3 when you plug it back into this equation. You'd have to get 3 equals 3. So if we were to go graph all these points at a 0-degree direction, go out 3 units from the origin, we say, okay, well, that would be this point here. At pi halves, which is up here, we'd go 1, 2, 3 up, and then left 3 here, and then down at 3 pi halves we would go out 3 from the origin here, and then at 2 pi we would still be at 3 from the origin. So we get this graph that looks like this, and you can see how this would be the most quintessential circle, and this is when r equals 3, and we'd say this is the graph of r equals 3. One thing that we should probably do, at least in this video, we say r equals 3. We can go over to Desmos, we can graph this r equals 3. You'll notice we get a circle of radius 3 centered at the origin. If we were to actually take that r value, and I think if we change this, you could see that r equals a, where a is some slider here. You can see how that's just going to be some circles centered at the origin, and the radius is going to change. Okay, so these next two graphs we're going to look at here, r equals a cosine theta and r equals a sine theta, there are just a few things that I kind of want to generalize about these things here, starting with this. When you talk about cosine and sine, these are functions here that in terms of their output are always going to give us some output. I'm going to say a y value, like an output. Sorry to bring up a y value here in a polar equation, but we say the outputs of this cosine variable here are going to be between -1 and 1. And maybe I should just write cosine theta. And we say that the outputs down here for at least the sine part of this are going to be -1 to 1. So we say whatever sine spits out, it's going to be between there and there. So we can see, I hope already, that a is just going to be some value that when we multiply these values by that, it's going to inflate or deflate our graph. We call it a dilation, okay, transformation. So, or stretch, we call it stretch, okay. So we're going to take a look at the r equals a cosine theta by using the graph of r equals, and we'll do 2 cosine theta. And I just want to kind of talk about, before we get into the general shape of these, how you would graph these in general. We would say that we're just going to throw in a nice battery of values here. I'm going to go by pi fourths this time, just out of convenience. We say 3 pi fourths, and I'm only going to go up to pi, and we'll talk about why here. And then I get to 2 pi, or 4 pi fourths, or that would be pi. Sorry, we're going to pi, aren't we? So anyways, plugging these in, we would say, well, the cosine of 0 is 1, so 2 times 1, we're going to get a 2 here. If we plugged in pi fourths, well, the cosine of pi fourths is root 2 over 2. And when we take 2 times root 2 over 2, you get the 2's to cancel, you get root 2. At pi halves, cosine will be 0, so 2 times 0 will be 0. And then this is going to start to creep back again. We'd say, well, then this is going to be root 2 over 2 times 2, but that's just root 2. And then we would say that we get 2 here again because the cosine here is, actually, let's be careful here. If we plugged in pi, cosine at pi is -1, and this would be negative as a matter of fact here. We get -1 times 2 is -2. So as a matter of fact, we probably could run through all of these, but what we're basically doing is if we went and graphed all these points, we say 2, 0, that's a 0, or not a 0 by the way, but 0, 2 here. We say in a 0-degree direction we'll go out 2 from the origin, and then, you know, if I go out root 2, pi force radian measurement here, we'll go out root 2, which is 1.414, that's about roughly right here. And then we would say at pi halves, when we're facing up here, it's a 0, so we're at the pole, we're at the origin. And if we're facing 3 pi force, now the interesting thing is 3 pi force is this way, but since our r value is -1.4, you know, ish, we're going to go backwards here, 1.4 ish. And then, you know, at pi here, if we were facing over here in this direction, we would have to actually walk backwards 2 here. So what we get is this graph that, you know, is, if I'm going to point this out here, it's a function of theta. We say this is r equals 2 cosine theta. Okay, you'll notice that it goes out 2 from the origin at most, okay, and it presents a circle here that is symmetric, and I do want to point this out here, with respect to the polar axis, okay. So any cosine graph is going to be symmetric with the polar axis. I'm going to say in general that the maximum r value here is going to be equal to the absolute value of a. I don't want to write that as an equation, but we'd say that a, well, this was 2, max r equals 2 here. Over for our sine equation here, we're going to get a circle that basically has a radius of, I'm going to say a here, and we get a graph that's symmetrical about the vertical axis, but this would be r equals a sine theta if we would say that max r equals a. So what I want to do is basically I want to go over to here to Desmos, and I'm going to say this. Instead of r equals a constant, we say r equals a cosine, and we'll say of an angle theta. And what we're going to see here is our cosine graph, as soon as I put in a slider here, that is symmetrical with respect to the horizontal or the polar axis. When I make a bigger and bigger, you'll notice that a is directly corresponding to what the maximum value of r is. And so you could see here 8.4, this is roughly 8.4 here. If I were to go out to 10, we see it has a radius of 10, and it's symmetrical with respect to the x-axis, where the moment that I go back up here and I make this a sine function, you'll notice that we have the same circle symmetrical with respect to the vertical axis and with the direct radius of this a value, whatever that vertical stretch is, okay? So there's about one more thing that I want to do in this video, and that's this: open up the door for a being negative. What would happen? What do we observe here? A is that maximum r value, but what does a do when a is negative? Well, you'll notice that our graph here actually, instead of opening upward, say it's a sine graph that has vertical symmetry here, instead of opening upward, it would open downward, but you'll notice that the radius here, if a was -4, the maximum r value is still going to be a maximum of 4. So we notice that negative a values would cause a sine graph to kind of open downward, whereas if we had a cosine graph, which is, you know, again, symmetrical with respect to the x-axis here, if a is negative, it's going to kind of open to the left. So we would say that if we were to make a graph then, more procedurally, what would this look like? Okay, so now that we've made some observations about this, and I kind of know that my r equals -5 sine theta, some things about this, like the maximum r value is going to have to be 5. I know that it's going to, well, sine is, you know, symmetrical with respect to the vertical axis, so if it's negative, the a value, instead of opening up, it's going to open down. So let's talk about what we know here. In terms of filling these graphs out, often we like to ask these questions here. So these are pretty basic, starting with this. This is a circle. And I'm going to say, because it's a function of sine, I'm going to actually mention this here, vertical symmetry. Okay, I didn't leave a line here for symmetry, but we often list symmetry as well. So we say the maximum r value is going to have to be 5 here. Now the number of zeros, to find zeros, how do we find the zeros for a function here? What we actually want to do is we want to just set this equal to 0 and solve for this. So we're going to use those as some significant points down here. Let's go ahead and set r equal to 0 and say -5 sine times an angle equals 0. So the first thing, of course, we would do is divide both sides by -5, which really doesn't affect the 0 on the left. But what we're really asking for is, would there ever be a time where sine is equal to 0? So if we took the sine inverse of both sides of this equation here, we'd say sine inverse of the sine of theta, we would get then that the theta here would be equal to the sine inverse of 0 radians. So in other words, where does sine ever equal 0 on the unit circle? I think it equals 0 here and here when it's on the ground. So we would say that there are 2 zeros that I can think of. We could list several of them, but I would say one's at 0, one's at pi. You'll notice if we go back to 2 pi, we're kind of just repeating ourselves here. But I'm going to go ahead and put 0 up here. I'm going to say, you know, theta at 0, r will equal 0. I'm going to leave a blank between these, as a matter of fact. I'm going to go out here and I'm going to say, and at pi. r was equal to 0. Because between these, I'd like to have at least one input value between my two zeros to see how it's behaving. So for instance here, I'm going to list up here, by the way, we get 0, pi, and that's good enough there. I suppose we could say 2 on a 2 pi interval, but if you wanted to be thorough, you could list 2 pi and just be coterminal 0. But looking at this, we would say, plugging in pi halves, what is the sign at pi halves? And the sign at pi halves, ladies and gentlemen, is 1. We get a sign value of 1. So we would get 5 times 1. Well, this is going to be our 5 here. So we notice that's our key point. So we would say that putting this graph together, we would say, well, facing in a 0 radian direction. That's what this is saying. We're going to go 0 out from the origin. So I'm going to be at the pole, right at the origin. We say in a pi halves direction here, it's going to go 1, 2, 3, 4, 5 up, but we kind of already knew that, didn't we? We say in a pi direction, it's going to be back at the pole again. So we get this circle here that's kind of like you're going to have to, it looks like a deflated balloon or a sad balloon, but you get this circle here that has vertical axis symmetry, a max value of, r of 5, and a couple of zeros here. We said at 0 and pi. If we were to go around all the way to 2 pi, essentially, it would just have negative outputs and then kick itself back around, But that's how you make circles in the polar coordinate system. In the next video, we're going to look at some other special polar coordinate graphs. Cheers.